Good morning, ladies and gentlemen. Welcome to the video on inflection, shape and the second derivative. Before we go into those items, I'd like just to quickly remind you what we've covered already in terms of stationary points. We know that if the first derivative is equal to 0 and there's a sign change, for example from positive to negative slope, we have a maximum. If it's from negative to positive, we have a minimum. If it's from positive to positive and yet it still goes through 0, then we have this weird sort of point here that we call a stationary inflection. And we're going to talk about more about what exactly a stationary inflection is in this video. But first, let me talk about the second derivative. Now, the second derivative, I think, is quite a simple concept, at least algebraically. Graphically, it makes it a little more difficult to interpret. First of all, the first derivative to this is 4x takes 6. The second derivative is you just do the same again, so it's 4. Now note, here we use the second derivative to determine whether something is concave down or concave up. Now, concave down is this function here. Note that the first derivative is minus 2x and the second derivative is minus 2. The second derivative being negative means the slope is decreasing all the way along the curve. So even though the second derivative is negative, the slope can be positive. See there? That's a positive slope, but it's decreasing because it's going from 2 to 1 to 0 to minus 1 to minus 2. So when the second derivative is negative, say less than 0, we can say that the first derivative is decreasing, or the slope is decreasing. It might still be positive, but it's decreasing. Conversely, or convexly, concave up, convex, 2x, 2. When it's positive, it means the slope is increasing. So here, it's negative, it's less negative, so it's increasing, it's 0, it's positive, it's more positive, so it increases the entire way around. Note there are lots of these little cutouts from the textbook, so please feel free to print off the OneNote. Essentially, when the second derivative is negative, a function is concave down. Think negative, unhappy face. When it is positive, it's concave up. Alright, so an inflection point is when there's a change in shape of curvature. So it goes from concave down to up or up to down. And that can happen in two different ways. Either we can go from here to here, or that there is concave up and concave down. Note we've seen this type of inflection point before because the gradient is equal to 0. So when f dash at a certain point is equal to 0, that's what we call a stationary inflection point. This one here is a non-stationary inflection point because the tangent at the turnover point from concave down to concave up is not equal, does not have a slope of 0. Alright. Using a sign diagram, this is stationary inflection point. You see how the first derivative doesn't have a sign change, it goes from negative to negative. However, the second derivative does have a sign change because the second derivative is concerned with the curvature, and this is going from concave up, smiley, to concave down, frowny. So there's a sign change in the second derivative, but not in the first derivative in terms of a stationary inflection point. Alright. Here, though, there are several things happening. At x equals b, the slope goes from positive to negative. That's what's happening here. Positive to negative in the first derivative, you should be thinking max. Then, when we go from negative to positive, that there is indicating a minimum, and that's happening at c. Note how point A doesn't appear at all in the f-x. They don't have to have the same critical points, because here is a non-stationary inflection point. And this non-stationary inflection point is indicating when we're going from concave down to concave up. So from negative to positive on the second derivative. And that's what's happening at A. So I guess in summary here, when the first derivative is equal to 0, 4 things could be happening. Either it's going to be max, min, stationary inflection point. Note that there is no sign change on these stationary inflection points. They're either negative, negative, positive, positive. Here, when there is an inflection in the second derivative, they might be non-stationary, going from negative to positive, positive to negative, or in this case here, positive to negative, negative to positive. So we need a sign change for a stationary point of inflection regardless. Well, need a sign change in the second derivative for a point of inflection. Alright, this is a very typical type of question. Find and classify all the points of inflection. So, to do this, we look at the first derivative, f dash x, which is 4x cubed minus 3x squared, and then we look at when this is equal to 0. And what we should notice is we can factorize this quite comfortably by taking out an x squared, and what we're left with is 4x take 3, and therefore our solutions for x are 0 and 3 on 4. So our sign diagram for f dash x has critical points at 0 and 3 on 4. And now we can sub in values here. If we sub in, say, minus 10, it's going to be a pretty negative. If we sub in minus a half, or positive 0.1, positive 0.1 here is also going to be negative. If we sub in here, we have a positive. So what we're expecting to happen is to have negative slope flattening out negative slope, positive slope. So we're thinking here, at x equals 0, there should be a stationary point of inflection, and here, at x equals 3/4, there should be a minimum. So what we can say is, well, the point when x is 0, and we can sub 0 into there, so y is 5, is equal to a stationary point of inflection. Stationary point inflection, you can write it in full. Then we can sub in 3/4 into there, which is not going to come out beautifully, so I'm just going to write it in shorthand here. 3/4 and whatever f of 3/4 actually is going to be a minimum. So that's a stationary point of inflection and a minimum. Now let's consider the second derivative. The second derivative is f double dash x, and to get there we take the first derivative and do it again. So 4x to the 3 becomes 12x squared take 6x. Now we want to solve for where it's equal to 0 to find the critical point, so 0 equals 6x bracket 2x take 1. Our solutions for that are x equals 0 and a half. Zero and a half. Now let's consider what happens either side. If we put in minus 1, it's going to be positive. So when you're thinking positive, you're thinking smiley face curve. If we put in x equals, say, 0.1, 0.1 squared is 100th, 12 hundredths take 6/10 is going to be negative, so it's going to there. And then after here, we can put in, say, 1. 12 times 1 take 6 times 1 is going to be positive. Alright, so what's happening is when we sub in x as 0, this point here, 0, 5, there's a sign change. We already knew that. We know that's a stationary inflection point. But one we didn't know before is when x is equal to a half. So when x is equal to a half, and what f of a half is, remember we're using the original function to get the y value, there is going to be a non-stationary inflection point. Right. Now, let's attempt to see what that looks like graphically. So, this here is our original function. And I'll zoom in a little to give you some better information. You can see here at x equals 0, our original function had a 5 in the end. I've changed that to a 1 on here by accident. the 1 on the end or the 5 on the end, just move it vertically. So I'm sure you're comfortable that if I change that 1 to a 5, this graph would stay the same shape, it would just shift up. Anyway, this lets us see it more comfortably because it's down here at 1. You can see that there is a stationary inflection point because it goes from negative and the slope goes back to negative, but the concave convex changes from concave up to concave down, and then at some point here it changes back to concave up, and we're going to concave up all the way through. This here is the first derivative. When the first derivative is 0, the slope is 0 at that point, and here, when the first derivative is 0, the slope is 0. So we can see that there is 0.75, that there would be that x equals 0.75. So when the first derivative is equal to 0, slope 0 on the original function. Now let's look at this second derivative. When the second derivative is equal to 0, the slope on the first derivative is equal to 0. Hectic, huh? Alright, when this here is 0, we see that lines up with the stationary inflection point. So note how there's this double up of zeros. A double up of zeros in the first and second derivative will always indicate a stationary inflection point. Here, though, when the second derivative is equal to 0, the original function changes from concave down to concave up. That there is a non-stationary inflection point. So going through the features of this curve again, we have here a stationary inflection point where the slope of the original graph is 0. Because the slope of the original graph is 0, the first derivative is 0. And because it's going from concave up to concave down, here the second derivative goes from positive to negative, hitting 0 at that point. Going across to here, second derivative hits 0, so up there, directly above it, is a non-stationary inflection point where we go from concave down to concave up, from negative to positive here. I really hope you can see my cursor. And then here, when the first derivative is 0, there is a turning point. Note the second derivative doesn't have anything to do with the turning point because the concavity stays the same the whole way through here, it doesn't change. Alright, sorry this has been a long video, but it's an important concept to get because then we apply it to trig as well. Alright, the other thing they can ask you to do is sketch f-x and f"x given the graph shown. Alright, so let's think of f-x, or let's point out some key features. Clearly, that there is a min. Here, there is a non-stationary inflection point. Non-stationary inflection point. Nisif, I just made that up. Did I say minimum? I meant maximum. Clearly that's a maximum. Here is the minimum. At some point here, there is another non-stationary inflection point. And at some point here, there is a stationary inflection point. Alright, now note, where there are inflection points, the second derivative needs to be at 0. Okay, so let's do the second derivative first. There's no set order you have to do them in. Actually, no. Let's do the first derivative first. Okay, first derivative is concerned with largely with max and min, or where the slope is equal to 0. So where the first derivative has a max, it must go through 0 here, it must go through a 0 there, and it must go through a 0 here. Before here the slope was positive, and after it's negative. So it would go something like this. Down, up, down. Not beautiful, but the important thing is we're getting the key points right. And that there is that. Let's change colour. I might go to really light blue for the second derivative. Where there are inflection points, the second derivative must be 0. So the second derivative here will be 0 at that inflection point, it will be 0 at that inflection point, and it will be 0 at this inflection point here. Here is concave down. Concave down means we're negative. This bit here is concave up, we're positive, we're coming over here. This bit here is concave down, and that from then on is concave up. So the second derivative looks something like this. Now note, we could stretch that out, but it's going through those critical points that count. Alright, thank you very much.